Okay, we have come to the third lecture on hydroxyl compound. Tomorrow will be the last lecture, okay, and tomorrow I will only have about 40 to 45 minutes for lecture. The remaining time will be spent on giving you guys an important briefing. So today, my aim is very simple. I hope to finish until the activity of the law. Okay, so in order to reach this aim, we'll do it together as a team, okay? And I always believe that learning is a process of forgetting. So whatever I told you last week, probably you have forgotten some, if not all. So I'm going to do a quick recap on the reactions that an alcohol can undergo, right? First and foremost, alcohol, organic compound, all organic compound in the presence of excess oxygen can be combusted to form what? Carbon dioxide and water. So the challenge for you guys is to write balance equation. So when we ask for balance equation, the number of atoms on left hand side and right hand side must be equal. Okay, state symbol depends on the question. Okay, if you are unsure, best is not to give state symbol, right? Up next, okay, we also look at how alcohol can undergo reaction with sodium metal, okay, just like your water and sodium hydroxide. So the product that you obtain in the case of alcohol is that of a sodium salt. We call it sodium alkoxide. Okay, the word alkoxide, ALK, okay, ALK depends on the number of carbon present in the alcohol. So let's say if you use ethanol, then the salt that you produce will be sodium ethoxide, right? And in this case, we have the production of hydrogen gas. How about alcohol with sodium hydroxide? Okay, in this case, we learned that alcohol, despite the presence of polar OH bond, it is actually very weak acid. In fact, okay, it will give you a pH of 7, neutral. Okay, so that's why even if we try to react with sodium hydroxide, there is no reaction. Also take note of this. From O level, you learn that alcohol and carboxylic acid, they can react to form ester. So in this case, we look at the reagents and conditions. So other than your carboxylic acid, okay, it will require the use of concentrated sulfuric acid as the catalyst, because this esterification, okay, is slow and reversible. So in order to maximize the yield of the ester, we need to use corn sulfuric acid as the catalyst. Okay, and at the same time, we will need to use heat. Okay? So in view of this drawback, in view of the fact that esterification with carboxylic acid is a slow and reversible process, how can we ensure a complete reaction? Very simple. We use a reagent that is more reactive than your carboxylic acid, and that comes in the form of acid chloride. So in this case, when you use acid chloride, being more reactive, okay, it means that your condition will be milder. Hence, you can use it under room temperature. Okay. In the last lecture, I have also given you guys the type of reaction. So very important. I hope you have copied down. If not, please ask from your friends. So all these reactions that you see here, okay, we can classify it as the cleavage of O single bond H, right? Up next, okay, alcohol can also be reacted with your sodium chloride, corn H2SO4 under heat to form your alkyl halide. Okay. Here, other than this reaction which we see in the lecture on Rx, okay, you can also use this particular reagents and condition. Corn HCl, zinc chloride catalyst under heat. Okay. This, in theory, it works for primary, secondary, and tertiary alcohol. But in reality, when we want to carry out the experiment, we normally use this particular reagent and condition on your tertiary alcohol, because this will favor the SN1 reaction pathway. Okay? So other than this particular reagent and condition to get your Rx, we can also use PX3. So if you want RCl, we use PCl3 under heat. If you want a milder reaction condition 10, you use PCl5 at room temperature. Okay? In order to minimize the number of steps involved in purification, we can go one step further. Instead of using PCl5, we can use SOCl2 at room temperature. And for this particular reagents and condition, you notice that the side products form HCl fumes, white fumes, SO2, your gas. So they will just escape from the reaction vessel. Hence, okay, the Rx that you obtain will be largely will be of high purity. Okay. So the important thing I need you guys to pay attention is that for the third reagents and condition, PCl5, okay, you cannot use PBr5, you cannot use PI5. Why? Because PBr5 and PR5, they are unstable owing to steric hindrance. So in other words, they cannot exist in the first place, right? If they cannot exist in the first place, you cannot use them as your reagents and condition. As for SOCl2, some of you may ask me, hey Mr. Ting, can I use SOBr2? The answer is no, because SOBr2 is also unstable. Okay? So in the event that you need to synthesize RBr or Ri, okay, the only reagents and conditions that you can use is either PX3 under heat or NaCl con or NaBr con H2SO4 under heat or NaI con H3PO4 under heat. Why con H3PO4? Please go and look at your Group 7 lecture notes. Right? So other than alcohol undergoing nucleophilic substitution, it can also undergo elimination, right? So in this case, in the presence of excess corn sulfuric acid at 170 degrees Celsius, your laboratory conditions, okay, you are going to form alkene. This is nothing new. And all these reactions as stated on the screen, we can classify them under reactions involving the cleavage of CO single bond. Alright? Also, okay, if we were to have primary alcohol in the presence of oxidizing agents like like KMNO4 or K2Cr2O7, okay, in the presence of acid H2SO4, under heat, the alcohol will readily be oxidized into your carboxylic acid. Okay, so previously we also learned that there is an intermediate product, and that is your aldehyde. If you want your aldehyde, what do? Very simple. We use a milder oxidizing agent in the form of K2Cr2O7. Okay, and in this case, there is a slight change in the condition. You need to do immediate distillation so that you can get your aldehyde. So this part about immediate distillation, okay, is important. Don't miss it out if you want your aldehyde. For secondary alcohol, when it undergoes oxidation, it forms ketone and the reaction stops. Why? Because in ketone, you notice that here or here, you don't have a hydrogen. So without the hydrogen, it cannot be further oxidized. So it stops at ketone. How about for tertiary alcohol? What happens when you have tertiary alcohol? Can you oxidize it? Daryl, can you oxidize tertiary alcohol? No, right? Because in tertiary alcohol, you don't even have a hydrogen attached to the carbon that bears the OH. Okay? So here, the lesson that we can learn is that you can use oxidation to distinguish between your primary, secondary, and tertiary alcohol. Okay, so this is a good distinguishing test for primary, secondary, and tertiary alcohol. And last but not least, I also introduce you to this new concept, which is your triiodomethane test, aka isoform test. Okay, so I say that the equation you must memorize because it is always asked in test or exam. Okay, to help you with your memory. Okay, you know you guys like to chase after pop stars with numbers, right? For example, S4, then what? S Club 7, right? And then last time you also have your Liu Liu, right? Correct? So now I also give you a set of numbers, okay, for you to idolize. So that will be in the form of 4, 6, 5, 5. Okay? Here, you may ask me, okay, on the left hand side, 4 and 6, how do I know which reactant is 4, which reactant is 6? Correct? So now, you know that it is 4 iodine, 6 hydroxide ion. But in test or exam, when you are panicked, how would you know? Very simple. On the right-hand side, on the product side, you know that you form 5 iodide and 5 water molecule. Okay, 5 iodide. Don't forget that the other product will be your CHI3. So 5 iodide plus 3 iodine in the CHI3, altogether 8 on the right-hand side. So on the left-hand side, it must also be 8, isn't it? So that's why 4 is given to your iodine. 4 times I2 gives you 8 iodine atom. Oh, so that's how we remember your 4655, right? And after last lecture, I think there are some concerns like, here on the reactant, right, when you use this particular alcohol, you notice that there are 2 carbons. But after the reaction, you notice that here it is 1 carbon less. Okay? Yes, you are right to say that. Why? Because one of the carbon, the one highlighted in blue, after the reaction, it forms your CHI3. So in the remaining part of the organic compound, it is 1 carbon less. And for triiodomethane test, okay, it is also known as a step-down reaction because after the reaction, the number of carbon atoms decreased by 1. So previously in RX lecture, you learned about Cn minus. Okay, when you use Cn minus for nucleophilic substitution, it is known as a step up. Why? Because the number of carbon increased in the product, so step up. So now in this case, it's step down, right? So some of you may ask me, how do I know? How would I know carboxylate and the CHI3? How are they formed? The thing is, the formation of carboxylate and CHI3, you don't need to know for A level. You don't need to know how to describe the mechanism for the triiodomethane test. Nonetheless, okay, in the spirit of learning, I'm going to show you how this may be formed. So, if you don't mind, okay, please turn to your annex, which is page 28, right? Page 28. So this is the actual mechanism of the triiodomethane test. So in the very first step, you notice that you have the alcohol reacting with your iodine. In iodine, you have learned it under group 7. So in group 7, you know that the halogen molecules, they have oxidizing property. They can act as oxidizing agent. However, okay, the oxidizing ability decreases down the halogen. So when you reach iodine, it is actually the weakest oxidizing agent among the rest of the halogen, isn't it? So in this case, because it is relatively weak, that is why the oxidation is only until carbonyl compounds. Okay, you will get your carboxylic acid. So here you notice that I have my carbonyl compound. This particular fragment seems familiar. Where have I learned this from? Okay, if you were to turn back to page 14 of your lecture notes. Sorry, 15, page 15 of the lecture notes, this part. This is where we have seen it, isn't it? So the last time around, I tell you guys that other than the alcohol fragment, okay, the carbonyl fragment as shown up there can also give you a positive isotope test. So now you understand, this is how it comes about, okay, from the mechanism itself. So going back to page 28, the mechanism. Okay, for step 2, step 3, I think it is very boring just to look at the screen, just to look at the lecture notes, right? I'm going to give you some animation, some motions, okay, to engage you guys. Okay, so now we start off with the oxidized product, which is your carbonyl product, and let's see how on earth do we get our CHI3 and the carboxylate salt. Okay, so now here comes the OH minus, okay, your base. So as you can see, it removes a H. Okay, it deprotonates your organic compound. It removes a H plus, okay, to be Exact. It deprotonates. Okay. So once it deprotonates the H plus, what happens? The excess electron can now attack, can polarize the I2, and this particular reaction is similar to that of your electrophilic addition, the attack on the delta positive iodine. So this process repeats itself on another 2 times. So you notice that on this particular carbon, okay, will eventually end up with your 3I. Okay, so there you have it, okay, the 3I on the carbon. So now comes the 4th OH minus. So now OH minus will attack the delta positive carbon. Okay, here this particular carbon is attached to oxygen, so it will have a delta positive charge. So when it attacks, let's see what happens. Okay, your CX3 leaves as CX3I. No, CX3H, right? Okay? So that is how at the end of the day, okay, you get your yellow PPT here, CH3, yellow PPT, which is the observation that you should write down if you were to use this as a distinguishing test. At the same time, okay, given the fact that it is carried out in alkaline medium, that is why you have a salt, a carboxylate salt, instead of carboxylate acid. Okay, so I hope this part you are clear on this. So having said all this, okay, we go back to our exercise that I asked you guys to try out over the weekend. Right, exercise 3, okay. First and foremost, nomenclature, IUPAC name. So what is the name of the organic compound A? What is the name of organic compound A? What how? Oh, we never do. Denise, what do you think? Organic compound A? Yes, Denise, S12. Huh? Butanol. So do you think butanol is accepted as the answer, butanol? Who thinks that it cannot be accepted? You guys are really very funny. Given the chance to talk, you all will talk. When given the chance on your own to talk, you will talk. When I give you the chance, you don't want to talk. So the thing here is you cannot just write butanol. Why? Because it is ambiguous as to where your OH is being placed on the carbon atom. So the correct answer in this case should be butane 1-O. Right? So here you notice that in organic compound B, the OH group is found on the second carbon atom, and hence it will be butane 2-O. And for compound C, okay, you notice that you have a 3-methyl group attached to the carbon that bears the OH group. So here, identify the longest continuous chain, and at the end of the day, you realize that the naming is 2-methyl propane 2-O. Okay? So now that you have named the compound part B, you are supposed to distinguish, i.e. distinguishing test between A and B. Okay, so you look at the condensed structural formula of A and B. Is there any obvious difference that you can see? Is there any obvious difference that you can see? So remember just now I did the recap, right? I said that, okay, to distinguish between primary, secondary, and tertiary alcohol, we use oxidation. So let's see whether we can use oxidation or not. So here, what is the type of alcohol? Primary, secondary, tertiary? Primary. How about this? Secondary. So if you were to use oxidizing agent, would you end up having the same observation? Yes, right, because the KMNO4 will decolorize. The purple KMNO4 will decolorize, isn't it? So now, okay, we cannot use that particular approach. So what else can we use? Is there any obvious difference that strikes you? For some of you who are observant, you notice you have this thing over here, right? So if you have this particular fragment in the alcohol, you can use the what test? Iodoform test, yes, correct. So in your description of the method, okay, this is how you describe. You warm A and B separately with iodine and aqueous sodium hydroxide. Okay, you cannot say alkaline iodine. No, you must specify what is the reagent that you use to create the alkaline medium. Alright, and of course, many students, okay, they just happily write the reagents and they forget about the condition. So don't forget the condition. Okay, here you need to warm it. Why? To prevent the yellow PPT from re-dissolving. So now that we identify the test, we know that the observation will be whether or not is there the formation of yellow PPT. So for B, because it has this characteristic fragment, it will form your yellow PPT of CHI3. On the other hand, A will not give the yellow PPT. And here you notice that I've given you the equation, so you may ask me, am I supposed to write the equation for this question? The answer is no. The equation here is just to help you understand how do we write the equation if the question were to ever ask you for it. So this is an example, right? Okay, up next, we are supposed to distinguish between B and C. So B, okay, butane 2-ol. It is what type of alcohol is this? Secondary, right? Then how about for C? Tertiary. So is the difference obvious as to what distinguishing test we should use? Some of you I saw nodding your head, and that is to use your oxidation, right? So here what happens is that for B, it will be oxidized, hence there will be this the decolorization of the purple color, whereas for C, the purple color remains. At this point in time, okay, all of you are busy copying down my answer, right? I have a question for you guys. Is my answer entirely correct? No. Why? Why not? Okay, that's a level 1 answer. Come, give me a level 5 answer. Do you think my answer is correct? Come on, this is not the first time we are doing distinguishing test, right? We have seen it last year in J1. So when we use heating, can we use heat under reflux for distinguishing test? So that's the common mistake that you guys made, right? So here, just heat will do. Okay, so please remember, when you are asked to do distinguishing tests, very important, there are two things that you cannot write down. Number one, you cannot write no visible reaction. Okay? Number two, you cannot use reflux. Because in distinguishing tests, we are just going to use a simple chemical test. Simple. Okay? If you were to use reflux, it is an elaborate, it's a complex apparatus setup. Okay, all I want to know is whether or not you have this functional group of this particular product. As simple as that. Okay? And of course, here you notice that I have this equation which is not required. Okay, and at the same time, it is also not balanced. This equation given here is just your synthesis equation, the one that you would normally write for your synthesis question. Alright, are we done with this? Okay, done? Okay, I understand from the lecturer at CC side, okay, this is the question that he gave to the CC group in the last lecture. So in order not to shortchange you guys, I've also prepared the question. Probably you guys can take about 2 to 3 minutes to quickly work out the answer. Okay, don't worry, the question I will eventually upload to Ask and Learn, so you don't have to copy the question for now. The important thing is to read and attempt the question. Okay? So this particular question again is related to the reactions that an alcohol can undergo, right? So just now we have seen the various reactions that alcohol can undergo. So it will be a test of your understanding, right? So take a look, quickly note down the answer. For those who are lost, don't know how to approach this question, okay, let's look at the reagent. Here you are reacting with excess corn H2SO4 at 170 degrees Celsius. Sounds familiar? So what is the product that you are expected to get? Okay, so with that in mind, can you work out what are some of the possible products in this case? Okay, another clue for you guys is, I hope you remember the last time around when I talked about the dehydration of the dehydration of alcohol, okay? The carbon that has the OH group, okay, on the neighboring carbon, on the side-by-side carbon, okay, in order for elimination of H2O to occur, there must be the presence of H. So that's another clue for you guys. What is your fighting? How do you manage to identify which are the side-by-side carbon to the carbon with the OH? Do you manage to identify? Okay, come, let me give you an additional helping hand. Oh, I've run out of ink. Okay, never mind. Yeah. Okay, this is unexpected, but never mind. Okay, look at my pointer, right? Okay, so here what happens is that this and this can come out as water, right? Because the carbon side by side, correct? Alternatively, guys, look, here and here, side by side as well, so the water can come from these two. Okay? You also notice that here and here, they are also side by side, hence water can come out from here. So these are the three ways in which you can form your alkene. Okay, so the answer is as such. The important thing that I want you guys to learn from this question is the booby trap, which is sometimes they will ask you, oh, how many stereoisomers and structural isomers can be formed after this reaction? Also, don't forget, when you have stereoisomers, i.e., your geometrical isomer, your cis isomer, or your optical isomers, okay, it means that straight away you have two different products. So in this case, altogether you will see 5 products. The first 3 are presented here. Quickly write down your work, okay, check your work. So these are the first 3. Later on I will show you the remaining 2. And very important, okay, when you are asked to draw geometrical isomers, I hope you remember to use, I hope that in your answer you remember to reflect the trigonal planar geometry, right? Okay, very good. I'm a human, so I'm also prone to error. So actually here should be trans, this is cis. For those who copy blindly, please go and do some self-reflection. Okay, are we done with this slide? Yes? No? Any no? Okay, if not, the last 2 product is as such, okay? So essentially, okay, this concept is nothing new. We have already learned it under alkene. It is a matter of whether you remember or not. Okay, so now that we have come to alcohol, I hope you guys really embed this concept in your mind and don't lose it, right? So with that, for the alcohol part, we have already completed. So now let's move on to a new subtopic. Okay, are we done over here? Okay, are we done? Okay, this particular summary I have already gone through at the start of the lecture. Okay, so I'm not going to dwell on it. So now we go into this thing known as phenol. Okay, here I want you guys to take note. Phenol and alcohol, they are 2 different things. In fact, phenol is a functional group on its own. Okay, the functional group of phenol is OH directly bonded to your benzene ring. So take note, okay, phenol is a distinct functional group on its own. Alright, although there's the presence of OH group, it behaves differently from your alcohol. So here, okay, what are some of the physical properties of phenol? It is at room temperature, it exists as a colorless crystalline solid, okay, and it is corrosive. So at room temperature, it exists as solid. It means that it has a high melting point, isn't it? Right? It must be high melting point, that's why it exists as solid, right? So what is the reason accounting for the melting point? What is the reason accounting for the melting point of phenol? So using your SASE template, structure, attraction, strength, and energy required template, okay, we try to explain why phenol has a relatively high melting point. Okay, so phenol is a polar simple covalent molecule that has hydrogen bonds between the molecules. Okay, these hydrogen bonds are relatively strong under ambient conditions and hence require a larger amount of energy to overcome, and this explains why phenol has a relatively high melting point. Okay? So same thing, whenever you are asked to explain melting point, boiling point, it is your SASE template. So, like what I mentioned before, anything highlighted in green, please fill in the blanks. So now, okay, we have OH directly bonded to a benzene ring. Is it soluble in water? To answer this, okay, let's carry out an experiment and see what happens. Are you done with the copying? Okay, so let's see. We do experiment. Okay, so this is your phenol, exists as the solid form. Okay, so now we add in the water and stir the contents inside the boiling tube. Let's see whether the white solid dissolves or not. So now what happens when we have hot water? You notice that it becomes more milky, right? More cloudy, right? Correct? So actually what happens is that here, okay, in your lecture notes, okay, if you are looking at phenol itself, okay, if you are looking at phenol itself, the benzene ring directly bonded with the OH directly bonded to the benzene ring, it should be soluble in water. Okay. Just now the example is to tell you that sometimes, okay, the question may give you alternative data, so you are supposed to respond accordingly. So that is the data response question. However, let's say if it is an explanation-based question, okay, like for example, why is phenol soluble in water? Then this is how you explain. Okay, the energy released from hydrogen bonds between phenol and water is sufficient to overcome the hydrogen bonds between water molecules and hydrogen bonds between your phenol molecules. Okay, so the catch of this is that so just now we see the white, the cloudy solution. This is what is stated in your lecture notes as well, right? And one important thing I want you guys to take note of is that if your benzene ring is attached to more and more benzene ring, okay, the non-polar portion will be more significant. Okay, the ID-ID interactions will now become more significant, and that will hinder the dissolution of this compound in polar solvents such as water. Right, so pay attention to that. Okay. Same thing, I'm going to go back to my video, right? Okay, previously I tell you guys that your alcohol, for example, ethanol, is a very, 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 very weak acid, right? So like the saying goes, seeing is believing. Let's see, how do we know that alcohol is a very, very, very weak acid? So here you have your ethanol. Okay, your ethanol. So let me fast forward a little bit. You're using your universal indicator to determine the pH. So you compare the resultant color change with the benchmark. You notice that it matches that of pH 7. So ethanol is neutral, right? What's the joke that you guys have? So now, how about for phenol, you may ask. Okay, so let's see what happens in the case of phenol. Okay, so now we have phenol, we do the same thing, we use the universal indicator. Okay, you notice that it is like orange kind of color, which means to say that it is actually acidic. And just now, during the comparison with the benchmark, you notice that here, in this case, it is about pH4. pH4 is, the pH value is for a weak acid. If you have a strong acid like HCl, okay, the pH value will be 1 or 2. So in this case, we go back to our lecture notes, we look at the acidity of phenol. Okay? So phenol is a weak acid. What's the definition of a weak acid? You have learned it in O level. It means that there's a partial dissociation of H plus in water. Okay, so with your O level understanding, this is how you will represent the dissociation of H plus in phenol, correct? And since it is partial dissociation, you represent it with your reversible sign. Alright? This is how you will do it based on your existing O-level knowledge. However, later on, okay, when we learn about ionic equilibrium, okay, the more accurate representation is as such. So here what happens is that phenol will protonate water molecule to form phenoxide and your H3O+, hydronium ion. The hydronium ion is actually the real representation of H plus in water. H plus, there is no electron, so when it is surrounded by water molecule, the low pair of electrons of water molecule will form a dative bond with H plus. That's why you end up having H3O plus. So according to our lecture notes, yes, the pH value roughly about 5 to 6, okay? So the thing here is we want to do some form of comparison, okay? Previously, under alcohol, I tell you guys that alcohol is actually a weaker acid than water, correct? So now we bring in two other species, your carbonic acid, which is also a weak acid, and your phenol. We realize that from experimental value, from experimental results, okay, carbonic acid is a stronger acid than your phenol, which in turn is a stronger acid than water, and water is a stronger acid than ethanol. So this particular order of acidity, you need to know, okay? Then you ask me, for the values below, the 5, 10, 16, 18, the answer is no need to memorize, right? I need you to know the order on top. Okay, Ken? So now you ask me, how was this value? What's pKa? Okay, pKa, you will learn it later on under ionic equilibrium. For now, I'll just touch and go. Okay, what happens is that Ka is a parameter to measure the extent of acid dissociation. So the name for Ka is acid dissociation constant. Okay? Acid dissociation constant. So the greater the extent of dissociation, it means that your Ka value will be larger. When Ka value is larger, it means that it is a stronger acid. Right? It is a stronger acid. So now, what is pKa? Okay? The word P just represents minus log base 10, minus Lg. So when you log the value and you put a negative sign, okay, so it is the reverse. The smaller the pKa value is, the stronger the acid. Alright? So this is something which we'll learn later on in term 2 under ionic equilibrium. But for now, we need to have this in mind, okay, to make sense of this pKa order. Like, how come this one is 5, then I say that carbonic acid is stronger. Okay? For now, it is to help you understand this. This is very, very, very important. Why is phenol more acidic than alcohol? Why is this important? Because it is stated clearly in your syllabus that you can be tested on it. So better make sure you know how to explain it. Before I give you the real explanation, I want to define define some terms, okay? So from your O-level understanding of acid, acid is any substance that dissociates to form H plus when dissolved in water, correct? That's your understanding from O-level definition. So that O-level definition is otherwise known as your Arrhenius definition. Okay, Arrhenius as stated here. But we realize that in reality, okay, this particular definition, although it is good, but it is not all-encompassing, okay? It is not all-encompassing. There are certain situations, there are certain acid-base reactions which do not agree with your O-level definition. So how? We need a better definition, okay? So we are going to learn the Bronsted-Lowry acid definition. So same thing, this particular definition, we'll see it later on in ionic equilibrium as well. And you need to know how to define. So it's a matter of when you learn it. Right? So according to Bronsted-Lowry definition, okay, an acid is a proton donor. It gives out H plus, proton donor. Okay? So once it gives away H plus, the other product will be your anion, right? This anion is given a name. It is known as a conjugate base. Conjugate base. Okay? So if you want to know how conjugate base, like very abstract, okay, the definition, to put it simply, it is a proton acceptor which differs from your acid by one proton. Okay? So all this, if for now you think it is too difficult, never mind. Later on, term 2, we'll look at it again. But for now, I need you guys to know the definition of Bronsted-Lowry acid. Okay, it's a proton donor. So with this in mind, we can then explain the relative acidity between your phenol and ethanol. Are you all done with the copying? Are you all done? Okay, so people here, we want to compare the acidity between ethanol and phenol. If you are asked this question in test or exam, the very first thing that you should do is to write out the acid dissociation equation. The first marking point we are looking out for will be the equation. And that usually constitutes 1 mark. Alright? For question on explaining the relative acidity between phenol and alcohol, usually the question is about 3 marks. Okay, usually. So 1 mark will be given for your equations. Okay, so this is how you should present your equations. Ethanol reacting with water to form your alkoxide ion, okay, and phenol reacting with water to form your phenoxide ion. This is how you should present. So now, okay, in your lecture notes, okay, the second bullet point says that the relatively stronger acidity of phenol is due to the relative stability of the resultant anion. So to explain why a species is more acidic than the other, we look at the outcome. We look at the product that we obtain, the anion. Okay? If it is stable, it means that it favors dissociation, and hence it will be a stronger acid. Can I understand this part? I repeat myself again. Okay, if the product after the dissociation, okay, the anion is stable, it means that the forward reaction will be favored, right? Correct? That is why it is a stronger acid. Make sense? Okay, so now the next marking point is, why is it more stable? Why is the anion of one species more stable than the other? Okay, so in this case, what happens is that phenoxide, the negative charge on the O, can delocalize into the benzene ring. So when there is a delocalization of negative charge into the benzene ring, it means that there is a dispersal of charge. When the charge is dispersal, it means that repulsion is minimized. So that is why it is more stable. For those taking physics, I think you guys can better appreciate, right? The dispersal of charge means lower repulsion. Correct? On the other hand, for your ethoxide ion, hey guys, come pay attention. This part is really important. Ethoxide ion, the negative charge cannot delocalize. Instead, it is localized on oxygen. So when it's localized on oxygen, okay, it's going to be intensified and it is more likely to be attacked by electrophile, correct? Or in this case, okay, it is more likely to accept back your H+. Therefore, it is less stable as compared to your phenoxide ion. So this is the explanation. So for those words that I've highlighted in blue, these are all your key marking points. Okay, you need to have that in your answer. So my recommendation is to highlight whatever that I've highlighted on the screen. Okay? So, okay, I'm going to stop very soon. Let me finish the last part, okay? I promise I'll stop after this. Okay, the last part talks about carboxylic acid, your COOH versus your phenol. Before learning about phenol, okay, when we talk about acidic organic compound, sure away you think of carboxylic acid. Fair enough. But now that you have learned phenol, I want you guys to remember, phenol is also acidic. So when it comes to structural elucidation question, when it comes to that, oh, this product form is acidic, you have to consider phenol as well. Okay? So at the end of the day, how do we know whether is it phenol or carboxylic acid? This part here gives you the important clue. Okay? For carboxylic acid, it will react with your sodium carbonate or sodium hydrogen carbonate to give off carbon dioxide gas. But for phenol, this reaction does not occur. So this is the important clue that tells you, at the end of the day, this acidic organic compound, is it phenol or carboxylic acid? So here, I want you guys to write it down for use in structural elucidation. Okay? So for today's lecture, to summarize things, if we look for the first half, we do a quick recap of what we have learned in alcohol, specifically the chemical reactions. After that, we look at phenol, the physical properties in terms of melting point, melting point and solubility. And then after that, we look at the acidity property of phenol. Okay. Last but not least, the important thing is how do we explain the difference in acidity between your ethanol and phenol. This part is important. It has come up many times in exams, A-level, and before. Okay, I need you guys to understand that. So with this, okay, tomorrow I will conclude the lecture and you are free to go. Thank you.